Yes, just a minute. So we'll start the section. So in today's class, we will be mostly discussing on two different uh, problems that we usually encounter with data science. So that is, one is classification problem, and another one is regression or function approximation problem. So what does these two means? Right. So what kind of problems do we actually encounter with these? So let's see some examples first. So these are some of the problems that we have, which we can solve using um, data science. All right. All right. So let's say the fraud detection in a credit card transaction. So it's like flagging whether a transaction is a fraud transaction or not. Or other one problem can be distinguishing between a cat or dog. So what kind of problem that can be, or detecting a failure in a motor. So all these are like a yes or no questions or yes or no problem. And another one is understanding churn based on email communication. So all the first four problems that we discussed are like yes or no. The questions, the problem that we address is just yes or no. And when we come to the next four problems, like predicting the material property for different molecular structures or predicting scores of a cricket match, that can have um, a lot of answers, right? So, like predicting the reaction kinetic parameters or predicting the value of a board position in a game of chess. So, all those will have a number of answers. So, those type of problems can be called as function approximation, whereas these, like yes or no questions, or if it is a dog or is it a cat, such problems can be classified as can be called as classification problems. So we have three kind of learning in a wide manner. So first one is supervised regression. So it's kind of like predicting a number. So example is like rent or the price or how many minutes to complete a job or the score in a match or something. All those comes under supervised regression task. So these are the methods that are popular to us. We have the ordinary least squares, then the rich lasso regression, and polynomial regression. Whereas some other supervised classification problems are like where we have to predict a class. It's like if we use our model to train a lot of emails. So if you look at your email box, you can see whether a message will be flagged rightly in the spam folder. That's a classified classification problem, or predicting the class of an image, like if it is a cat or dog, or if it is a good image or bad image. All those comes under supervised classification problem. And some of the methods are logistic regression and KNN classification. Then we have another. So what is common between these two supervised problems is, or supervised problems are like we have the data, we know the target. So if we while training the model, so let's take the example of cat and dog images. So if you feed the image of a cat, then our final prediction has to be either class 1 or class 0. Maybe class 1 belongs to cat or class 0 belongs to dog. So we know what we have to do, right? Or what we have to predict in the supervised problem. Whereas in unsupervised problems, like we just give the model some data. So there are no labels at all. Like let's say we again have the cat and dog images, but we don't specify which is cat image, which is dog image, because let's say we don't know that, or you see, it's some kind of abstract patterns that we have in the image. So what is unsupervised? task that will do is like they will learn the patterns in the image or the data, and they do the uh, segregation automatically. So it's like some examples are like customer segments. So where we can classify these different customers or different document topics. Like if we put a bunch of documents, bunch of papers to the model. So some documents may be letters, some may be notice, or some may be email conversation. All those will be segregated. So one of the method is K-means clustering algorithm. So what is one question that separates them? So it's is that do you have the right answer for a training data? If it is yes, if there are numbers, then it is regression. If it is yes, and if they are labels, then it is classification. And if we don't know what these data represent, then we have the unsupervised clustering problems. So first, let's look at the regression problem. So regression problem is a supervised learning. So that builds like a functional relationship between dependent and independent variables. So one of two such problems which is very common are we will predict the property price, or we can predict in the stock prices. All right. So let's take the predicting property price as our model. So these are the independent features, right? So location, so it can be any place. Then size and area can be anything. Then whether the transportation facilities are available, then whether the house is furnished, utilities, and many other features it can have, right? So all these are independent features which will determine what the price of the property can be. All right. So the thing is, uh, a good location will have higher price, or if it is if you are living in a city, so if the transportation facilities like metro, everything, if they're nearby, then it will naturally attract higher price amount. So all these matters whenever we are predicting the property prices. So let's say for two types of regression problem. So one is univariate and another one is multivariate. So univariate is such problems that only one dependent and one independent variable. So let's say when we are talking about house prices, we are going to consider only the area of the house. So the only square footage is the criteria that we are deciding on how the houses will be priced. In that case is called as univariate problem. Similarly, if you consider one more feature, so here we had only one feature x and the target was y. If you have two features or multiple features or multiple independent variable, that is in here if you see we have x1, x2. So our house prices is decided by two different features or two different independent variables. Such problems are called multivariate problems. Then we have linear versus non-linear regression. So in linear regression, we take our relation between the independent and independent variable to follow a linear relation. So here if you see, even though these are our data points, so for this corresponding to this x, we have this y. So x and y, we have different values. So the best fitting curve, which is a straight line, is as shown. So if the curve that we are trying to fit is a straight line, then it is called a linear relation. Whereas if we go for higher order terms like so here if here this equation of this line can just be y is equal to ax plus b, where a and b are the parameters. Whereas if we go for higher terms like y is equal to x square plus bx plus c. Then we have non-linear relation. Non-linear relation comes from the higher order terms. So, bet so we'll have a better fit when we increase the order or the complexity of the problem. But it becomes difficult also to do the regression. So here we have some of the linear regression methods. So we have the ordinary least squares, then we have the ridge regression, the lasso regression, then partial least squares, and principal component analysis. So all these belongs to the linear uh, part or the linear regression methods. And for non-linear, we have the polynomial regression, then we have the neural networks and the spline regression. So what are the stages in a regression process? So we have the starting of the problem, then we formulate the problem. That is, we choose the set of variables, or we form the model, we decide the complexity of the model, then method of the fitting, and some of the assumptions that we need. Then we try to fit the model. So if we see this plot, so the final plot is as shown, or final relation is shown by the line. So whenever we start our fitting, it may not be the same. So the line can be, so let's say, so the line can be somewhere here, then here. So based on based on the equation, so if we have the equation ax plus b, so each of these lines have different a and b. So that makes the slope and the intercept different. So the final ax plus b will be choose based on the regression methods that we choose. So there comes the model fitting part. Then we have the assumptions or are valid assumptions that we make. So let's say, so here we have made some assumptions. So we'll validate those assumptions using the model. So let's say we want some of the points to be exactly on the line. All those things are validated. So if you're satisfied with that, then we can move to the evaluation, uh, evaluating the model. So where we see the goodness of the fit, etc. And if that one is also passed, we'll stop our regression and use our model for intended purpose. That is predicting the house prices or predicting the stock prices. If these were not satisfied, we'll again have to start our problem from the beginning, and we'll change the maybe if we have initially we have used a linear model, we'll move to a polynomial model that will increase the order of the problem. All those searches will do to get the desired output. So here we have the regression illustration. So yeah, so let's say we have a data set of car service center. So these are the cars and minutes. So it contains a number of cars, which is the number of independent variable, and minute for service. So if it is two number of cars, then the minute to service, the two number of cars is less than 50. Once the number of cars increases, the minutes also increases. So what our goal is to find the best functional relationship between both variables, which can be given by a linear line. So our model is a linear regression in this case. So let's see how all the least squares work in this case. So let's say, uh, so we have to fit any line, right? So this is our line. So let's say beta naught plus beta 1 xi. So xi, for each of these xi, we'll have a yi based on the beta naught and beta 1. That decides the line, right? So let's say this is our line, and so let's consider the first point. So this point we'll consider. So here we have the point. So for this point, if we substitute beta naught and beta 1 and the xi, we are going to get a point on the line or the value on the line. So the actual departure of from this point is given by this epsilon 1, which is the error. So if you want to get this point, we have to add the error along with this line. So that is true for each and every point. So error is nothing that is given by the distance or the departure of this point from of any point from the line. And also we have to so you'll also be thinking like why we are taking the error in this along the y-axis. Why not we take the error, let's say, in this fashion? So which is the least distance, which, because it's a perpendicular to this black line. But that is uh, because the uncertainty or the error is only in the dependent variable. We know cars is the independent variable in this case. So we are certain of the number of cars that we have, but we are uncertain of the time that is needed for the service to complete. So the error is calculated by the actual point, and we will put the xi in the line and we subtract. So that defines the error. Now we do the sum of squares of errors. So that is given by just squaring the errors and adding all the errors. So that is so this is the quantity that we want to find minimize, right? So once we have the errors for all the points, we want to minimize this sum of squares of errors. So the minimization of this sum of squares of errors gives the estimate of beta naught and beta 1. So here is the equation for that, beta 1 and beta naught. So how do we reach at that equation? So it's just a simple calculation. So what we need to do is we need to minimize this result. So what we have to do is first we have to take the partial derivative of this equation with respect to it's a beta naught, then with beta 1. So we will get two equations. On solving those two equations, we will finally end up with the result. We end up with these two equations. Now testing the goodness of the fit. So once we have fitted a line or a curve in our data, the goodness of the fit is tested by the R square method. So R square is a metric that is used, which is used to determine the goodness of the fit. So R square calculates the variability in output variable calculated by the input variable. So if you look at this equation, so this is the total variability in Y. So this is the actual data and this is the mean, and this is the variability of the prediction. Okay. So if these two are same, then this will be sorry. So yeah, if these two are same, then we are going to get R square is equal to 0. So which is a bad fit because uh, the variability in the Y is also followed by the variability in each of the measurement. So that will naturally gives a bad fit. But if our Y prediction is actually equal to the true value, then the numerator is going to be 0. In that case, our R square will be equal to 1, which gives a perfect fit. So this is another equation for the same, but this is the another adjusted R square value, which also takes into account the number of independent variables. So if you have the n as the total number of variables, then p becomes the number of independent variables. So why we never score a model on its training data, right? Okay, so why is it so? So every R square or accuracy or error we have seen so far, that we have measured on the same data, the model was fitted. That number is not a performance estimate; it's a measure of memorization. So if we already, so let's say the classic example of exam. So giving the students the exam paper to revise from and then setting the same exact paper does not tell us whether that student have learned anything or is just memorizing the things. So that is the same thing that we do with our models also. So what we do is we'll first use the training set to make the model learn, and we'll use some other locked away set which has not yet seen to be in our test set. And we'll use only the training set for fitting the data, and model never sees the test rows while learning or during the training process, right? And once the model is trained, we will make these scorings on the test set, and that number or that metric shows the honest estimate of performance of our model. Okay. So we should never look at test set whenever we develop our model. Now, another problem that can happen when training our model is underfitting. So let's say, so let's say, so so let's say this is our data. So we have data here, data here, data here, data here. It's kind of like a parabola. So if we have decided our data to be or a model to be linear model, and so however we try, our model is going to give us error. So which means our model is too simple to fit into this entire data. So it misses PL patterns, or it is poor on training data, and it will also be poor on testing data. But let's say because we have some knowledge and we increased our model to second order and we got a good model. So which means our fit is okay and it captures the patterns and it's put on both training data and test data. So these are two cases that happens whenever we build the model. Now we say we again um, try to increase the complexity of the model. So let's say our model had some points like here, here, let's say here, here, and here, and here. So we are trying to increase the complexity of the model again. Then what is going to happen is like it is going to follow each and every point. So it will be like so if the model is too complex or the model is having higher order, it will be excellent on the training data, but its performance on the testing data will be very poor. So, so the one metric that will show that if our model has overfitted is the R square value again. On training data, the R square will be very good. whereas when we test, the R square will drop very bad. So there's a large gap between the two, in the R square of training and testing. So whenever we train our model, we have to also test our metric on the test data. Now let's see k-fold validation. So sometimes uh, we may not have enough data to keep aside for testing. So one split. So let's say we have the data 100 data, and 20 we kept for testing, and the remaining 80 we kept for training. So one split gives one estimate, and so we may not know, right? So which data has landed in the test set or which has landed in train set. So the k-fold validation is a technique. So in this technique, we repeat the exercise so that every row gets a turn at being tested. So it's like we are in we without increasing the complexity of the model, we are making the model learn from the whole data without the need for huge amount of data. So here is an example. So here after a five-fold validation, so we have the different scores, and the mean of this metric is 0.77. But if you see one of the values that is 0.62, tells us that the model is unstable on some slice of the data. But so if we have not done this k-fold validation or five-fold validation, uh, that number would have been hidden from us, or we may not be knowing that or the distribution of our data. We might think that, so let's say we have done our split on the third split, and it gave a very good result. But if our real data is something of 0.62, then whenever we test our data on the real cases, it is going to give very bad result. So usually k is equal to 5 or 10 is a standard value to be used. A larger k means more training data per fold, and we need to do more experiments. So it's kind of like a hyperparameter, and yeah. So now we do have some questions. So you can speak. I think nobody wants to answer. Okay, so in a linear
The
regression
first
equation,
option will be change in the dependent variable.
what does the slope represents? Yes, the answer is B, and the coefficient of regression R squared is the proportion of variance explained by the model. Now let's say we have the data, so we have the X and Y. We want to calculate the best fit line for this. So do you want to try using pen and paper, or I'll just show you the solution. So I'll just tell you what all we need to be done. in this case. So first we have to start. So if you remember the equations, we need to know the y bar, x bar, right? So I think I will just go to the solution. So or else I will write. So we need to find the x bar is the mean of the x, then y bar is the mean of the y. Then we need to uh, subtract each of these x from x bar and y from y bar. And then we have to find x minus x bar whole square. Right. So first we have to find the mean. First we have to find the mean of x, then mean of y. Then we have to find x. Each of these x we have to x minus x bar, y minus y bar. Each of these with the mean, with the mean that we have found. Then we have to make the summation of so let's say minus 2.5 into minus 4.5 plus minus 1.5 into minus 2.5 and so on. Then divided by the total number. So we get 2 sxx and xy and xxx. Now the beta one will be given by sxy divided by sxx. So here we have, and we can use the formula to find the beta naught, which is y bar minus beta 1 x bar. So here we have the numbers. So this is our final equation. Now here is the r square value, so which is nothing but yi minus y bar whole square. So whenever we are finding this one, we have to substitute our x values in this equation, and we have to find the xi bar. Right. Um, so based on the last questions, what is the slope of the best fitted linear regression line? So the slope is given by 1.73. So that is 1.7. So here we have the equations which can be used to find the solution. Now if we use our x in the equation, we'll finally get the solution or finally we'll get the value of predicted y for x equal to 6. So if we have to use the equation, and we'll end up with the value. The r squared value also we know how to find it. So we have to substitute that in the equation. Now mean squared error is nothing but yi minus y bar whole square divided by 6. That's a residuals whole square divided by the number that will give the mean squared error. So this is just wording. So the slope of the linear regression line is given as 3. So the 3, so the x coefficient will be 3 and intercept is 2. So we have the plus 2. So this is the new equation. And for x is equal to 8, we have the solution. So we have seen different sum of squares terms. So let's see the relation between each of them. So we have sum of squares of errors. So that is nothing but the true value minus the predicted value whole square. Then sum of squares of residuals, that is the predicted value minus the uh, mean of the true value whole square. Then we have total sum of squares, that is given by the actual true value minus the mean whole square. So if you look at this relation, we can get that SST or the SS sum of square, total sum of squares is equal to sum of squares of errors plus sum of squares of residuals. We also know the R square equation. So the R square equation is nothing but 1 minus some error sum of squares divided by regression or the total sum of squares. So what does those actually mean? So SST means it's a total variability in Y. So that is how much Y varies at all. So that is the variation of the true data. Then SSE is unexplained, the residuals. That is what the model still gets wrong. So it's still, there are some errors that from the prediction. So SSC explains that, or SSC denotes that SSR or is by the regression, that is what the model accounts for. So again, we have the R square, SST. So we have to be, we have to explain, or you just have to know these formulas. We'll have problems following these formulas. All right. So which of the following formulas correctly calculates the sum of squares of errors? So if it is errors, mm, we have to think that think about the true and the um, predicted quantities. All right. So SSC we have seen it is the option B. And then which equation relates SST and SSC? So SST is equal to SSE plus SSR. And also SSE is equal to SST minus SSR. So A and D both are correct. So what are the possible values of R squared values? It varies from 0 to 1. Then if SSE equal to 200 and SST is equal to 800, what is the value of R square? So we know the equation for R square is equal to 1 minus SSE divided by SST. So the value of R square will be 1 minus 2 by 200 by 800. That will be equal to 0.75. Yeah. So if the linear regression model perfectly fits the data, what would be the value of SSC? So if it perfectly fits the data, all the data points will lie on the line or the fitted curve. So there will be no errors. So the total value of the SSE is the true minus the predicted will be equal to 0. And what happens to R square when the regression models fit improves? We know R square determines the fit of the model. So R square will increase. Yeah, R square will increase. Yeah. All right. Now let's see the hypothesis test on regression coefficient. So in order to check if the linear model's fit is good or not, we can test whether the estimate beta 1 is sufficient or not. So our null hypothesis is beta 1 is equal to 0, and our alternate hypothesis is beta 1 is not equal to 0. So when beta 1 equal to 0, our model reduces to just y1 or predicted value is equal to beta naught plus the error, whatever the error it predicts. Then our alternate hypothesis where the beta 1 not equal to 0 means that our full model prevails. So we'll check both the cases. and we'll see the R square. So this is not needed. Okay. So that is about regression. Now we'll move to the classification problems. Okay. So the classification, as we have already said, classification is also a supervised learning that aligns class to the data points. So one example is like emails, spam detection, sentiment analysis, image classification, medical diagnosis, fraud detection, and language identification. So we have our model. So this is an online classification problem. So whenever we load a model to our drive or OneDrive, or if you receive a mail with an attachment, this PDF classifier will classify the document into different classes. So it may be invoice, it may be a CV or a proposal. And so then if we attach or some AI agents works in this part of our pipeline, invoice may be directly uploaded to accounting, or CV may be used to notify the recruiting or the HR department, or proposals may be directly forwarded to the concerned departments. So what are the types of classification we have? So it can be a binary classification where we encode only two different classes. So it may be one side is circles, one side is crosses. So this is a binary classification. Then we have multi-class classification where more than two classes are involved. Then another category of classification is linearly separable problem. So if the two data can be separated using a line, such cases are called linearly separable problem. Or if a nonlinear boundary is required to separate the points, then such problems are called nonlinear separable problem. Now we'll see the logistic regression. Even though the name is a logistic regression, but it is a classification technique. So here, given a new sample, so we have to predict whether the sample belongs to class 1 or class 0. So if it's a binary classification problem, the probability by which we can guess a new class is half, right? So it can be either class 1 or class 0. So simply guess of a class is not a good way to classify the sample. So hence probability is introduced to provide better understanding. So what is logistic function? So sigmoid function is otherwise called as logistic function. So here we have it. So here is the function that is fx is equal to 1 divided by 1 plus e raised to minus x. So to classify two classes, we use decision boundary or a linear equation. So the value of this equation can be varied from minus infinity to plus infinity. X can take values from minus infinity to plus infinity. But what our goal is to bring this into 0 to 1 range. So whatever the value the x takes, the final value will be from 0 to 1 when we use this sigmoid function. So at x is equal to 0, e raised to 0 will become 1. And this is the point where we have f of x is equal to 0.5. So that is the threshold, or anything that comes beyond that. So this will be considered to be in a separate class, and whatever comes below this point, below that threshold, will be considered to be in another class. So in this logistic regression, we have a linear boundary equation. So this is our equation. So beta naught plus beta 1x. And we use that sigmoid function in this line. So if we apply the sigmoid function, what we end up with is 1 over 1 plus e raised to minus beta naught plus beta 1x. So if you take the cost function, or if you define the cost function as such, then if our y is equal to 1, we will use log minus of log of this function. And if y is equal to 0, then we use minus of log 1 minus of this function. So if you can see this, so this is our decision boundary. So it is continuously learning to separate separate different classes. So at epoch 0, it will be, so let's see, at epoch 0, it starts from somewhere below. Then on continuous epochs, it will move such that all the classes or all the points belonging to the same class falls on one side of the line. So here we have some questions. So what type of machine learning problem is logistic regression primarily used for? Even though logistic regression has regression in it, the name, but we should not fall for it. So logistic regression is a classification algorithm used to model the probability of a binary outcome. Okay. Then in logistic regression, what is the output range of the logistic function? We know logistic function is a sigmoid function, so the range is from 0 to 1. Now, what is the purpose of the sigmoid function in logistic regression? So the main purpose is to fit or normalize our values. That is to normalize our values between 0 and 1. In logistic regression, what is the cost function that is minimized during training? So that is something that we have not. So this is the cost function. So this is called as um, cross entropy loss function. All right, in logistic regression, how are model coefficients typically determined during training? So that is so it is calculated using gradient descent method. So which evaluation metric is commonly used to assess the performance of a logistic regression model? So since it is a classification problem, we cannot determine using the metrics that we have explained in regression like R square, MAE, or RMSE. So we use this accuracy, precision, recall, etc. So we'll skip this. So we have seen some metrics that we have discussed, like accuracy, precision, etc., in terms of classification problems. So let's see what that is. Okay. So this one, so this matrix or this column is usually called the confusion matrix. So here we have the actual class that is positive or negative, then we have the predicted class which is again positive and negative. So if an actual positive class is predicted as positive, it is called as true positive. And if an actual negative is predicted as negative, it is called as true negative. So what if an actual negative is considered as positive or the model predicts it as positive, then it is called as false positive. Similarly, a true positive, if it is considered as negative or predicted as negative, then it is a false negative. So, can you think of a situation where this false negative can be highly dangerous? So, when we were in pandemic, COVID, so if an actual case was positive, and if our test has given it as a negative, predicted it as negative, then it is an actual problem that we have. Whereas if a negative COVID patient was falsely um, given as a positive, uh, that is wrong, but still it is not as impactful if a true positive case is considered as negative. Usually, what happens is whenever we have negative and if the result is positive, we usually go for second testing or second opinion. But whenever if a positive patient is given a negative, we wait at least for 1 or 2 days before going for another test. So precision is a metric. So precision is given by the true positive divided by a true positive plus false positive. Then sensitivity is given by true positive divided by true positive plus false negative. So in COVID case, the sensitivity had to be very high so that the true positive rate, false negative rate is very less. So that sensitivity increases. Then we have specificity. Specificity is true negative divided by true negative plus false positive. So here we have. So if you remember this step, these columns, it is very easy to um, learn or remember these metrics. So it's nothing but true positive and adding all these will give the sensitivity. Similarly, specificity and negative predictive value is given by true negative divided by true negative plus false negative. And accuracy is a measure of among all the measurement, how many are the true predictions. So true negative and true positive will come in the numerator, and all the numbers will be at the denominator. So here we have um, numbers and examples. So here we have the accuracy is given by true positive plus true negative divided by all. So it's so the accuracy is pretty high here, 0.925. Then precision is given by true positive divided by true positive plus false positive. So it's by 90. Then we have the recall. Recall is nothing but sensitivity is otherwise called as recall. So it is given by true positive divided by true positive plus false negative. That is given by 80 by 85. It's 0.941. We have FN score, which is the harmonic mean, and the specificity is given by 0.913. So why only so if you look at the all these metrics, the accuracy actually takes in all the values and gives a metric. But why it is not reliable or why it is not advised to only look at accuracy? Suppose one transaction in 1,000 is fraudulent, and model that predicts not fraud every single time is 99.9% accurate, and it catches nothing, right? So, but its recall is zero. So whenever the classes are imbalanced, quote, we have to always quote precision and recall, never accuracy alone. So what is the purpose of a confusion matrix in classification? So to visualize data in 3D space or to measure the accuracy of a model, you assess the performance of a classification problem. So what is the So as you have seen, the confusion matrix gives all the metrics related to the classification problem. So it is used to access the performance of a classification model. In binary classification, what does precision measures? So precision measures identifying um, positive instances. So what it is actually. So it's a ratio of true positive to all positive predictions. So if you remember the table, so this is a predicted. That's a ratio of true, true positives to all the positives predicted by the model. That is the precision. So in a binary classification problem, if a model makes 80 true positive predictions, 10 false positive predictions, 5 false negative predictions, and 1 is 0.5 true negative predictions, what is the accuracy of the model? So accuracy is pretty easy to calculate. So we have to see the true positive and true negative, add those, then divide by the whole numbers. So that will be 80 plus 105 divided by 200. So that will, so we have already calculated that in the previous slide. All right. Then the next is a classification model predicts 120 instances as positive, out of which 100 are actually positive. So what is the precision of the model? So that will be nothing but 100 divided by 120. So it will be 0.8. So what is the right metric, right? So already we have seen the examples. We have discussed the examples. So a spam filter. So a false positive sends a real email to spam folder, right? So if we received a lot of emails, maybe one of the email was very important to us, but it is falsely given as a spam, or the spam flag is positive for that email, then it goes to spam folder and we will miss it. So missing one spam is a, but so let's say one of the spam comes to our main inbox. So that is not a big problem, right? But missing one of our important email is a problem. So in case of spam filter, we have to optimize precision because a false positive is expensive in here. And let's say in cancer screening, just like the COVID case that we have discussed. So a false negative sends a sick patient home untreated. And a false positive means one more test, which is unpleasant, but it is not fatal. So in such cases, a false negative is expensive. So sometimes a false positive can be expensive, and sometimes a false negative can also be expensive. So there is one more problem. We cannot maximize both. So we have to design our model or design the decision threshold so that we can catch more positives, that is recall. Then the recall rises, then the precision falls, or we have to, if you raise the threshold, then the reverse happens. That is, moving the threshold is exactly what raises out the uh, false positive or the false negative counts. So there is one curve called as ROC curve. It is the receiver operating characteristic curve. So let's say what it is. So it's a graphical representation or it's a symbol graph that shows how well a yes or no machine. So our classification is a yes or no machine, right? So it's either true or false. Let's say so. It's whether a yes or no machine learning model or a test case can tell things apart. So let's say let's going back to our disease example. So we have sick versus healthy person or a spam versus real email. So it uh, plots the true positive rate against the. So here if you see it's plots the true positive rate against the false positivity rate, right? So what the graph actually shows the true positivity rate. So how often the test is right when the answer is right. So in this case, a perfect classifier will have the true positive rate always equal to 1 and false positivity rate will be equal to 0. So the area below the curve has to be maximized. So if we uh, change the threshold, so let's say, so this is the actual threshold. So here, if you keep threshold at 0.5, whatever comes above 0.5 will be at one class, below 0.5 will be into another class. So the moving that slider or threshold changes how strict the test is. So if you look at this, a good curve, a good test always curves up high towards the top left corner, which will make the false positivity rate 0, a true positivity rate equal to 1. But meaning that it gets the many right answers with very few mistakes. All right. So if a classifier has a true positivity rate of 0.9 and a false positivity rate of 0.1, 0.15, what is the specificity of this model? So specificity is given by 1 minus false positivity rate. So it will be 1 minus 0.15. So the answer will be 0.8. Then a classification model has 122 negatives. So 122 negatives and 30 false positives. What is the false positivity rate of the model? So false positivity rate is equal to FP or false positive plus false positive divided by false positive plus true negative. So that will be 30 divided by 150, which will be equal to
0.20.
0.26. Yes. Now let's see the KNN. So KNN is a classification algorithm. K nearest neighbors is a classification algorithm that operates on very similar principle. So we'll see the examples. So let's say the D red points are horse and blue points are dog. So if we uh, put a new point, so these green dots are new data points. So we are asking whether it is a dog or a horse. So if you look at the figure, we can easily say that this belongs to a horse and this belongs to a dog. But what about this point? So that is where the question comes. So the training algorithm of KNN is we store all the data, then during the prediction, calculate the distance from X. So calculate distance from X to all points in your data. So that is one way, or then sort the points in data by increasing distance from X, then predict the majority level of K process points. So if you look at this point, and let's say we draw a circle around it. So if you draw a circle around it, what happens? The circle will be equidistant if this point is center. Then if more number of red points are there in the circle, then we label this point as horse. Or if there are more blue points, then we point this one as dog. So what actually makes this classification is the radius of the circle. Sometimes increasing the radius will make more number of blue or more number of red to be present. So our KNN in the KNN, K means the number of points that we set as the threshold. So let's see this. How choosing the K value will affect a class. So here star is the new data set. So if K is equal to 3, so let's say this is our circle. So we have two number of purple dots and one yellow dot. So that makes, if we choose our K is equal to 3, so this makes our star to be classified as class B. Now if we choose K is equal to 6, then the scenario changes because now we have more number of class A near the star. So that makes our classification to be class, our points to be in class. So the decision depends on the number that we choose. So this is another example. So if K is equal to 1, how different areas will be classified, and if K is equal to 5, how the decision boundaries will be made. And again, on increasing the K, we can see that decision boundaries are changing, and with a large number of K, we can see a clean decision boundary, but we can see more number of red points in the blue area. So what is the approach, or how can we fix the number of K? So if K is too small, if K is equal to 1, then every point is its own neighbor, uh, or that does not make any sense. Like it only depends on one point because a single mislabeled point creates its own region. Whereas if K is too large, every point participates in the prediction process. That is also not used. So the practical rule is like try a range of K, then plot test accuracy against it, and pick the elbow. So we'll see what is the elbow means. Then we use out of distribution K for, so we use odd number of K for two classes. So a vote tie cannot occur. That is like if you have two classes and if you use 3 points, then either of the classes gets the majority. And also we have to first scale the features, and because in this case, if you do not scale the feature, then the distances might not be, it will be meaningless. So KNN, some of the advantages are, is a very simple model. Then training is trivial and works with any number of classes, easy to earn more data, and it has very few parameters. But there are some disadvantages also, like a high prediction cost. So if the data set becomes large, then we have to take the distance with respect to each of the data. And if you use large, higher number of k, makes the prediction costly. Then if the dimension of the data is high, so let's say, so yeah, in all these examples, we have seen only the data with two dimensions, that is in x and y axis. So in the actual case, it may not be true. There can be more number of features ranging anywhere between a higher up to 100 features or something. So in such cases, it will be very difficult, or the computational cost will be higher. Then categorical features does not well work with K. That's also one problem. So which of the following statements is false about K nearest neighbor algorithm? Is false.
So
So
not in use for regression.
yeah, that is the false statement. Because it can be used for regression also. In regression also, the idea is the same. So if it just so what is the difference between regression and classification when we use KNN? So let's say we have so let's say so regression is all about numbers. So let's say we have one here, two here, three here, four here, then five. So these are the actual function values. Then if one point comes here, then if we choose the k to be 3, then it will take the average of the nearest values. So that is how the regression works for uh, when using KNN algorithm. Then which of the following is not true about K nearest neighbor classification? So the answer is D. So the explanation is like it's not the property value of the object, it's the class membership in term if it is a classification problem. Okay, so we have data from a survey. So this is next one question. So we have data from a survey and objective testing with two attributes A and B to classify whether a special paper tissue is good or not. So here are four training samples given in the table. So now the factory produces a new paper tissue that passes a laboratory test with A is equal to 3 and B is equal to 7. Then in our KN, we are choosing K is equal to 3. Then good is the classification. That is good, the classification of this tissue. So how to see this? So we have new tissue paper where A is equal to 3 and B is equal to 7. So what we have to do is either we have to plot it and see which are the three nearest neighbors, or mathematically how we can do it. So this is A, B. So we have to find the square distance to the query point from each of the point. That is 7 minus 3 whole square plus 6 minus 7 whole square. Similarly for all other points. So we have 17, 25, 10, and 10. So this is the distance that we have. Then we have to rank the distance. So here we have 1, 2, and 3, 4. And let's see, we have the two goods in the first two ranks, and third one is bad. So since our k is equal to 3, our majority is good. So we can classify this new tissue paper as in the category of good. So that was KNN. Now we have K means clustering. So K means clustering is an unsupervised learning algorithm. So that will attempt to group similar clusters together in our data. So we don't specify which data is which. Like in the other case, we had the red belongs to horse or blue belongs to dogs. So that such labeling is not provided in this case. So what does a typical clustering problems look like? So it's like we'll put a bunch of data into a model, then it will cluster similar documents. So it clusters based on features or similar properties or similar physical groups. So let's say, so this is our data that we start with. So the overall goal is to divide the data into distinct groups such that observations within each group are similar. So if you look at this data, we can distinguish that here we have a group, then another group, another group, another group, and one big group. So how it is that? So here also the K denotes a number. So in this case, in this example, we have defined our K to be 5. So here are 1, 2, 3, 4, 5 classes. Whereas if you had given K is equal to 2, then maybe this whole thing will become, or the blue, dark blue will become one class along with some yellow points, and all these small clusters will be fall into another big class. So we have to choose the number of clusters a priori so that the number of groups will be decided. Then we randomly assign each point to a group. So this is the algorithm. So each point will be assigned to one of the clusters. Then we'll calculate the distance between all the points and the clusters. We have techniques to do that. Then if the clusters stop changing or the centroid or the cluster centroids stop changing, we'll put our algorithm to a stop. So for each cluster, we'll compute the cluster centroid by taking the mean vector of point in the cluster, then assign each cluster data point to the cluster for which the centroid is the closest. So you can see it here. So this is our data. So in step one, we'll randomly assign. So here we have three classes or three clusters. We randomly assign each of the point to one cluster. So, and we calculate the centroid. So if you see all the centroids are closer to each other, then what we do is we find the distance between each point to the centroid, and we'll reassign the data points so that the centroids are recalculated. Now, on recalculating, the centroids move to different clusters. And again, we repeat the step, and finally, we will have the separated clusters. So this is how the choosing different K value affects our clustering. So here we have the blue. Here we have the cluster is 2, then 3 increase to 4, 5, and 6, 7, 8, and maybe 9 clusters. So we have here. So again, how to choose the K value? So there is no easy answer for choosing the best K value that we will see. So the one way is the elbow method. So what we are going to do is, let's see what the elbow method is. So first of all, we have to compute the sum of errors for some values of k. So let's say we start from the lower value from 2, then we goes to 4 clusters, 6, 8, etc. So we'll compute the errors in each of these cases. Then the SSC, so SSC we have already seen the sum of the squares distributed between each member of the cluster and its centroid. Okay, now we are going to plot this SSC against K. So we'll see that error decreases as K gets larger. It's because when the number of clusters increases, they should be smaller, right? So their distortion is also smaller. So if you see here, if this was a centroid initially, so all these blue points had to slide changing. So so if this was the centroid, then all these blue points had to calculate the distance with respect to this red point. Whereas when we increase the number of clusters, then the centroids changes or centroids move closer to the points. Then the number of or the distance of the points to the centroid will reduce, so that the error will also get reduced. So let's see this graph. So when it was two number of clusters, the error was high within the group sum of squares. Then when we increase the K values, you can see that the error is reducing. After it reaches 6, the reduction in the error is smaller. So it's kind of like our hand. So if this is our, so let's say, so if we draw our hand like this is our hand. So that's why this is called an elbow method. This is our wrist. Okay. So this is where the elbow is. So it's kind of like our hand. So this is why it is, so that's why it is called the elbow method. So idea of the elbow method is to choose the K at which the SSC reduces abruptly, as we have seen here. So that actually produces an elbow effect in the graph, which is quite evident in the picture. Okay. So some of the things that we have to um, know about K-means clustering. So random starts give different answers. That the algorithm begins from uh, different randomly placed centroids, and it can settle into poor arrangement also. So it's always best to take an ensemble that is run several times and keep the best. And it always try to find spherical or similar sized clusters. Then always remember we have to scale the data first, and it's also for KNN also, because we are calculating the center to distance centroid. So if one of the feature is in hundreds and one is in one of another is in 1, then an unscaled features can uh, cause errors. Then what what actually defines a good cluster? That is another question. So there is a metrics for that also. So a good clustering algorithm will provide high quality clusters in which the intra-class, that is the intra-class similarity is high. That is within the class, the similarity is high, and the inter-class similarity is low. That is between the two classes, the similarity will be less. So we are already seeing the elbow method. Now there is another one called Silout score. So Silout score. So Silout score is another metric which measures how a data point is to its own cluster versus other clusters. It's like if one we will consider each data points, then we'll calculate the distance of that data point within the cluster and to other nearest clusters. Then the Silout score can vary from -1 to 1. Always 1 is the better clustering. So what Silout score balances is the cohesion, that is within the cluster, and the separation. So both will be taken care of. So the um, formula for Silout score is Sx denotes the Silout score. Then it is Bx minus Ax divided by maximum of Ax or Bx. So let's see what is Ax and Bx. So Ax is the average distance from X to all other points in the same cluster. So Ax always calculates the distance from X to all other points in the same cluster. So that has to be less, right? So if one point is in a cluster, its average distance from X to all other points in the same cluster has to be less. Ideally, then Bx is the lowest average distance of X to points in another cluster. So let's say we have 3 clusters. So we have cluster 1 here. So this is one cluster. Then we have another cluster. Then we have another cluster. So let's say our point is blue in color, and let's say it is somewhere here. So this after training, our blue point is somewhere here. So it did load. Okay. So we have the blue point there. So we have the blue point here. So we are calculating the Silout score for this point, blue point. Now, if we calculate AX, AX is going to be higher, right? Because it belongs to the blue cluster and the distance is large, whereas the BX will be smaller in this case. So BX will be, it can be the distance between X and all points in red, or the all points in green, whichever is smaller. But since Bx is smaller than Ax, it will be a negative in the numerator, and the maximum will be Ax. So it will be negative divided by some value. So it is going to give a negative value. So the Silout score is bad. Whereas if we if you're trying to calculate the silhouette score of the new red point, so the red point is within the red cluster. So the distance or AX will be calculated based on this cluster. Then we have this green circle where we calculate the green is the cluster which is near to red. So BX will be calculated based on that. So BX will be greater than AX. So here we have a positive number and the maximum will be BX. So positive by the maximum will give a positive number. So if BX is quite far from A, or if the clusters are very far apart, then the difference will be quite a much. So BX minus AX will be higher. And so the value will move towards the ideal one. So so we have seen the elbow method as well as the silhouette method. So when to use the elbow method? So it's like a quick heuristic tool for estimation of K. So it works well with low dimensional data or well separated clusters, and it is efficient for large data sets. And when we have to use the silhouette method or silhouette score, it is useful when we have overlapping clusters or the boundaries are fuzzy, and also it provides a more objective criterion and handles a smaller or complex data sets. But it is slower because it has to calculate the distance between each of the points and from the nearby cluster. All those things has to be done. All right, then we have some of the questions. So which of the following is a goal of clustering algorithm? Is it visible? Yeah. Which of the following is a goal of clustering algorithm? So is it classification, regression, dimensionality reduction, or grouping similar data points together? So the correct option is option D. Then in k-means clustering, which of the following techniques can be used to address the sensitivity to the initial placement of cluster centers? That is, we have to use different initialization and running the algorithm multiple times with different initialization and selecting the best solution. So then another set of questions. In k-means clustering, what is the purpose of the silhouette score? That is to determine to evaluate the quality of the clustering solution. Then which of the following is a limitation of k-means clustering in handling imbalanced data sets? So it assumes all the clusters have similar sizes. All right, so these are some of the things that you can remember. So in regression, we have discussed the ordinary least square method, which minimizes the true minus predicted whole square error. Then we have the B1 and B0, which are the coefficients or the values that we determine for the linear case. Then R square value, which varies from 0 to 1. And residual plots and all those things. And in classification, we have the linear boundary plus sigmoid function, sigmoid maps, any minus infinity to infinity points 0 to 1. Then the loss is cross entropy. It's not messy as we have seen in regression. And then accuracy lies on the imbalanced data set. Then we have seen the precision versus recall. Then we have distance-based clustering algorithms. K is classification. K means we have the clusterings and supervised. Then elbow and arrows and silhouettes All right. So that's it for today. And maybe I will keep one more extra section where we will see the coding part of this logistic regression and classification problems. All right. Thank you for joining. I'll end the meeting. Thank you.
Thank you, sir.